And we begin. So, we begin with nuclear fission and fusion, and we're going to finish up with nuclear equations. And so we start with nuclear fission. Okay, nuclear fission, the way I want you to remember this is the cleaving of a large nucleus into two daughter nuclei. Fission is division. This is how you're going to remember this compared to the other nuclear processes we're going to be dealing with. Fission is division. It is the cleaving of a large nucleus into two smaller nuclei. Here's how it happens. Here's what happens with nuclear fission. We have superneutron. Dun dun dun. All right. Superneutron. Superneutron is flying along, and he's got a lot of speed and a lot of energy, and he flies along and he collides with a locomotive. No, he collides with a 235-92 uranium atom. Almost. He collides with the U-235 atom and embeds himself inside so that it actually becomes a part of the nucleus. Notice that we go from 235 to 236 because we've added a 1, 0 neutron, right? However, this nucleus right here is very unstable. Okay, for a number of reasons. One, the shape just isn't right. The uranium nucleus doesn't like 236. I can't really explain why beyond that. But also, this neutron brought a whole lot of energy to get in there. Okay, so this is an excited state of uranium. It doesn't stay there. The uranium, in order to regain a level of stability, it splits into two daughter nuclei. Okay, it splits into 139, 56 barium, and (94, 36) krypton. Now, stop here for a sec. 139 plus 94 is what? 233. Now, what did we have to begin with, though? 236. Okay, we're missing what? 3 neutrons. Well, lo and behold, those dudes also come shooting out of the nucleus as well. So, this is the reproductive process of superneutron. No, I'm kidding, but he does create more superneutrons. Neutrons not drawn to scale. Okay, so here we have 3 1 0 neutrons. They have a mass of 1, the atomic number 0, and there's 3 of them. Okay, now guess what these 3 superneutrons do?
They do the same thing.
These do the same thing. These hit other 235, 92 uranium, 235, 92 uranium, 235, 92 uranium, and those three guys do what? Oh, I'm off the page, huh? Okay. These split again. Not necessarily. No, in fact, there's a number of different, there's like 57 different nuclei between like 39 and 62 that get produced in this process. There's many different products of this. All of them are possible daughter nuclei for a fission reaction. Okay, but the important thing here is in this process right here, we also release a whole lot of energy. There's a whole lot of energy that gets released here because some of the mass becomes energy. And this is, so all of this, the 139.56 plus 31 neutrons plus 94.36 krypton actually has less mass than this 236.92 that we start with at the atomic scale. And mind you, these are individual atoms. If this happens in an uncontrolled process in a lump of uranium, this whole thing goes like that and releases a ridiculous amount of energy. Now, no, okay. If all three of these guys also produce right, and this one releases and produces a daughter and 3 neutrons, and this one produces a daughter and 3 neutrons. What are these 3 neutrons going to do? Okay. Okay, these 3 neutrons. Okay, so now there's 9 neutrons, right? These 9 neutrons are going to split off, and they're going to go create 27 new neutrons. Those 27 neutrons are going to split off and create 81 neutrons. And those 81 neutrons are going to split off and they're going to create 243 neutrons. And those neutrons are going to split off and they're going to create 729 neutrons. This process will not stop until there are no more U-235 nuclei to fission.
So it's like the extinction.
Okay, and this is called a chain reaction. This is called a chain reaction. This is what happened. This is why, in the blink of an eye, so much energy was able to be released over the cities of Nagasaki and Hiroshima, and at the Trinity site in New Mexico, and over various test sites, and underground in Nevada, and underground underneath certain mountains in North Korea, and everywhere that they've ever attempted one of these things, this is what happens.
So, like, if there was a bunch of uranium in the ground and it got set off like that,
No, but that's actually very interesting. There is a region in South Africa that has a high concentration of naturally occurring uranium. No, it's okay. But it is the ground is very, very warm because there's enough uranium there to create a naturally occurring nuclear reactor. Okay, now, but it's self-stabilizing. That means that there's enough other stuff in the region that it starts to absorb these neutrons so they're not hitting other uranium atoms. So the fission process is going on. Okay, it's rather radioactive. Okay, but the fission process is going on, but it's not so much as to go uncontrolled that we're absorbing neutrons, and it keeps the process going without getting out of hand.
but is there like any given moment that all of a sudden everything is just
No, not unless we try really, really hard to do that.
So it could be like result in cancer or something, like standing on the ground.
I would recommend you don't go to that site for any prolonged period of time. Yes. Okay, so that's fission. Now there is a. I want you guys to know how to write the equation for this. So we've got this whole drawing. Back out a little bit. Maybe not that far. So we can see the whole thing. All right, and this is really all we need right here. So we start with 1 neutron, and it collides with a 235 uranium. It produces a 139, 56 barium, a 94, 36 krypton, and 3 10 neutrons. That is the nuclear equation for nuclear fission.
Like those exact. So does that mean whenever like something like this happens, there's like a bunch of krypton and barium running around?
Okay, not. There's more krypton and barium, but remember that these two daughters are not unique. These are not the only products of this reaction. Each fissioned uranium nucleus could turn into different products. Okay, I have a list of them here. They could turn into cesium and rubidium. They could, so really any pairing between atomic number 30 and atomic number 62, if the atomic numbers add up to 92, any pairing could take place. Okay, so as long as the atomic numbers add up to 92 and they don't get too small, okay, so its minimum number is I think 30, and the big number, then if the minimum number is 30, then the big number is 62 because they add up to 92. Any combination in between there is a possible daughter nuclei for the reaction. Does that make sense, you guys?
Yeah.
Okay, so it could be, so in this reactor in South Africa, okay, this natural reaction in South Africa, you find all kinds of these other elements within that range of atomic numbers. Okay, that brings us to fusion. Nuclear fusion okay, it happens in stars. Not only does it happen in stars, it is what makes stars. Okay, you go outside and see all the bright orb in the sky, that bright circle in the sky. You are looking at a continuous nuclear fusion reaction that has been going on for about 13 billion years. Now, maybe not 13, more like, maybe 7 or 8 billion years, because it wasn't there when the universe started, but it's been there for a long time. Constantly, for billions of years. There's that much fuel there. In fact, there's so much fuel there that the star is going to continue, our star, sun, is going to continue reacting for about another 5 billion years. Okay, so don't hold your breath for when the sun goes out. Okay, it's not going to happen for a while. Life on this planet would be so different from where it is now that we wouldn't recognize it to begin with. 2, we're going to be dead. 3, life on the planet the life on this planet would be gone long before the sun actually dies out. There's other reasons why, but okay. So it happens in stars, and it is 5 times. It is 5 times more efficient than fission. So, for every kilogram of hydrogen fuel we use for fission versus every kilogram of uranium fuel we use every kilogram for fission, as opposed to a kilogram for fusion, nuclear fusion will release 5 times more energy. Robert. Okay, so here's how it works. In the sun is a giant bag of gas. Okay, kind of like some people running for president, but okay, so we get a deuterium isotope. This is a hydrogen with an extra neutron in there. Remember that blue is proton, and blue is proton, red is neutron, right? Okay, and these two collide. Yes. Okay. These two collide. Okay, it's not so much that they collide as they are crushed into each other. The gravity of the sun is so strong that at the center of the sun, the pressures are high enough to force these two positively charged particles together to make the strong nuclear force hold on to them again. Remember how we had the competing forces, right? They get close enough, the strong nuclear force grips both of them, and it leads to a helium nucleus and kicking out a lone neutron. So the equation for this becomes a 2-1 hydrogen plus a 3-1 hydrogen makes a 4-2 helium plus a 1-0 neutron. And this releases a ridiculous amount of energy. Okay, even more ridiculous than fission. Okay, so what to look for? You start with 2 very small nuclei. You finish with and you finish with 1 slightly larger nucleus. The reason I want you to distinguish this is because I don't want you to look at this and think, oh, it's an alpha decay because it's giving off an alpha particle, right? That's an alpha particle. You remember that 4-2 helium is an alpha particle?
Yes.
Okay. Yes, technically this is an alpha particle. Yes, this would have a whole lot of energy to it. That's not what's going on here. It's not an alpha, it's nothing's absorbing an alpha particle, nothing's giving off an alpha particle, it's not an alpha decay. It is these two guys fusing to create a new helium nucleus. Does that make sense? Okay, 2 very small nuclei. 1 slightly larger nucleus. That's fusion. Okay. That's fission and fusion. You need to know these ideas that fusion happens in stars, that it's 5 times more efficient than fission. Okay. To turn this into a chain reaction is very, very difficult. And that's why we have a hard time harnessing fusion reactions here on Earth. We can make fusion happen, but we can't sustain it yet. And we're trying to figure out how to do that, because as soon as we do, this is the fuel. Hydrogen is the fuel. You could run the entire city of Los Angeles for a year on a glass of tap water. So, it is worth pursuing because the energy rewards are astounding, and we would be able to create so much electricity that it would fundamentally alter the economy of the planet. We wouldn't need oil anymore, ever again. So,
explain why it's not happening.
well, think about what happens in the sun. Remember, it's the gravity of the sun that's cramming all of the hydrogen in the middle of the star together. It's a star. It's the size of a star, and the only way it works naturally is if you have something the size of a star collapsing the nuclei in the middle of the star to make it happen. And so what creates a star is it's a balance between the forces of the exploding forces of the fusion and the collapsing forces of the gravity, and that heat creates more pressure cramming these things together. We need to create a similar condition here on Earth on a much smaller scale in order to get that same fusion process to happen. We're getting there. We're not ready to, the problem is we're not ready to use the energy that gets produced to refocus it back into collapsing more nuclei. That's the trick. And coming out getting more energy out of it than what we're putting into it to make it happen. That's the problem. Okay. So, we now need to go over our nuclear equations because we have 5 processes that we need to be aware of. 1. Okay, so nuclear equations. You are going to be expected to you need to be able to identify the process from the equation. You need to be able to identify a missing particle from the equation. So if I give you all the pieces of the equation, except for one part, it's got a blank right there, you guys need to be able to identify it. What's missing? Okay, using isotope notation. Isotope. For example, 4,2 helium. Okay. Equation 1. Is it's called alpha bombardment. This is what Rutherford did. Okay, Rutherford, he didn't know this because he didn't have the means to detect it at the time. But when he was shooting his alpha particles at the nuclei of gold foil, okay, with the very few of them bouncing back and the vast majority of them passing through and some of them getting deflected and all that sort of stuff, what he really didn't know is that beyond his significant digits that he was able to measure for, some of these nuclei were getting absorbed into the nucleus of a gold atom and transmuting it, creating something else. $79, right? Yeah, 79. That was my first real blunder there. $79. Okay. When he shot an alpha particle into the gold, okay, he created a new element. Called thallium.
Is it TI?
TL.
Yeah, cool.
Okay. He didn't know this was happening, but we have since discovered that this is a process. But the only thing I need you to know, you don't need to know that Rutherford did this, because he didn't discover it. This is just what was happening. What I need you to know is that this right here, because the alpha is on this side with the gold, that means this is getting bombarded with the alpha particle. Okay, this gold nucleus is getting hit with this alpha particle, leaving behind 281 thallium plus a 10 neutron. How do I know that this is the number, and this is the atomic number, and that's the mass number? Okay. Here's how we tell. This is our total mass, combining with this is our total mass. 4 plus 197 is 201. If we detect a neutron coming off, that means we're left with 200 here, because this 200 plus this 1 is 201. So the numbers across the top, these two numbers, always have to equal these numbers over here. Yeah? The mass numbers are conserved. The mass number on the left the total mass number on the left equals the total mass number on the right. Same thing with our atomic numbers. The atomic numbers on the bottom total up to the same atomic numbers on the other side. A neutron has no atomic number, so all of our protons would be in this nucleus. 2 plus 79 equals 81. Yeah? Okay, so what are you looking for? You're looking for an alpha on the left with a big nucleus. Also on the left. Alpha with a big nucleus, both of them on the left. That's what you're looking for. That'll be an alpha bombardment. Number 2. Alpha decay. And I'll give you the one that we've been practicing. Oh shoot. No, I already blew that. Darn it. That would have been okay. A uranium by itself. Okay, big nucleus on it by itself, solo, releases an alpha particle and creates 238 minus 4, 92 minus 2, okay, and another nucleus that's slightly smaller. Okay. This is important because we're going to have another reaction here that's going to create a 4-2 particle that's not an alpha decay. So let's check our work here. 238 equals 4 plus 234. Yeah? Mm-hmm. 92 equals 2 plus 90. Yeah, we're good there. Mass numbers equal, atomic numbers equal, we're good. Number 3, beta. Okay, I'm sick of black. Beta decay. Okay, our example before has been the 14,6 carbon. Okay, here's our beta particle. 14 equals 0 plus what? 14. 6 equals -1 plus 7. -1 plus 5 is 4. -1 plus 7 is 6. 7, we look at the periodic table, we see this atomic number. The atomic number is nitrogen. Okay, so what do we look for? -1 plus 7 is 6, right? Atomic numbers on one side equals the atomic numbers on the other. Okay? Beta on the right is a beta decay. Okay. Beta decay tends to not happen with larger nuclei. It tends to happen with smaller nuclei. It can with big ones, but it doesn't always have to. Okay? Right, so that's beta decay. Number 3. Number 4. Nuclear fission. Let's do this one. All right. We're going to practice this here. This is nuclear fission. What goes in the blank? Okay. Now keep in mind, this is 3 neutrons, right? It's like a coefficient for that one. There's 3 of those getting produced. That's going to be a total mass of what? 3 neutrons going to be a total mass of 3. Here we have a total mass of 146. They need to add up to all right, so this is 235 plus 1 equals 236 over here, yeah? So that means our total mass over here has to be 236 also. So 146 plus what plus 3 gives us 236?
87.
Okay, 87, good. So that's our mass number. Okay, our atomic number. 92 plus 0 here we have 57 plus what plus 0 equals 92. 35. Okay, you have 35, you go to the periodic table, you look at the periodic table, you find number 35, you see that it is bromine, and that's your, this is your nuclear fission equation. Okay, so to identify what kind of equation this is, okay, it's going to give you a large nucleus plus a neutron. On the left, yes. And on the right, we have two okay, so on the right side, we have two daughter nuclei that are roughly equal in size. Okay, as opposed to, you know, an alpha particle and a big. So it's not this over here. This is two daughter nuclei, but this is an alpha particle and this is still a really big nucleus. Over here, we have two nuclei that are roughly equal in size and they're medium-sized nuclei. You can tell by the atomic numbers. Okay, plus some neutrons. That's nuclear fission. Okay. Which brings us to number 5. Nuclear fusion. Okay, fusion doesn't just happen between hydrogens. It happens between two really small nuclei. On the left. Okay, helium is another version of, helium will also fuse. Okay, it's fusing right now in the sun. Hydrogen and helium are the two that fuse. Okay, and your result is a slightly larger nucleus. Okay, without being a slightly larger nucleus. Okay, just a little bit bigger than the two you started with. Okay, as if you added them together. 2 protons, total of 4 protons. That's there. 4 plus 3 is 7. If this is a 6, then we need a 1 there. Okay, those are our chemical equations. Those are the ones you guys need to know. So that's it.